This is a talk that is a little bit related to research that I've been doing with my good friend Will Burleson at USC, and a cast of characters of current and former graduate students that are all listed here. And this is a picture inside our lab. This is one of our little reactor bags on a shaker table. And that warms the cockles of my heart. But this seemed like sort of a better cover slide to show you guys. This Paris 2015, or sometimes called COP21, has come up several times here. This was really kind of a watershed moment in thinking about how to enact any climate change, not just legislation, but really solutions. And this was the very first time that all the countries in the world, or almost all the countries in the world, set a goal of what too much climate change is. It was set at about 2 degrees of global warming. There was a big debate about whether 1.5 might be the right one. What was absolutely shocking to me is that that happened within the first 24 hours of this meeting. Because in the decades in the run up to that, that was one of the most controversial things that people were talking about. Is, well, we don't know what too warm, how warm is too warm. Maybe we could do this, maybe we could do that. They jumped at the opportunity to define something because everybody wanted to get to the business of then negotiating a better deal for their company, or for their country, right? The idea was once you have a target, now everybody knew how they were going to be trying to beat the next country to get a little bit better deal for their economy. Because in all of these cases, people are only thinking about it as, how do I slow down my economy? Because fossil fuel emissions are directly correlated with how well your economy is doing. We'll see some slides about that as we go along. What I hope to show you is that's not the only possible way forward. You don't have to slow down your economy to try to think about ways to solve climate change if we can come up with ways to take the carbon out of the atmosphere in the first place. That's what I hope to give you a little bit of a perspective on here. It is not an easy problem to solve, but it is the problem to solve, I think. Okay, so this had the really inadvertent effect of giving us the shot at creating a carbon market somewhere down the road. Because once the countries all agreed, and this is what the target's going to actually be, at some point you're going to have to end up at this moment of, wait, I should price this. And so that's sort of lurking as we go along the whole way here. So this talk is kind of divided into 3 parts. And I can shorten any of them to see how we're doing on the time. But the first chunk is just why? What's up? Here are some basic facts of what's going on with climate change, how it is related to CO2. There are many different ways I could put these together. I'd like to put these together as just data. I'm not going to show you any model results that we have here. Actually, on one slide of something that happened in my lab, there's a little bit of a model. But nothing in this beginning part. This is just data about what's been going on here since 1880. So this is time on this axis over here. And this is latitude. So here's the equator. Here's the North Pole. Here's the South Pole down here. And this is a version of a curve I think many of you have seen over time, which is just how warm is it getting over the last 150 years or so. One thing I like about breaking it out into latitude so that it's not just all averaged together is you can see several telltale signatures here. First of all, gray areas are where we don't have data. This is a product from your federal government at work. This is NASA at the Goddard Institute of Space Studies at Columbia. And the first thing is that you can see that the poles begin to warm before the tropics. That is an absolute prediction of what it would look like to put more CO2 in the atmosphere. And the pattern that you see here, not just the absolute magnitude, is a clear result of putting CO2 into the atmosphere. The other nice thing that I think you can see is that it's not monotonic, right? It goes up and down, up and down, up and down. And in general, you're going from a wash from cooler over here to warmer over here. The scale down here, by the way, is nonlinear, so that's 3 degrees warmer, about 3 degrees cooler. So the thing that you all sort of know and have seen is cooler up to warmer. But what happens in the reporting is as you go from red to a little bit yellow, you'll see all sorts of stuff about, oh my gosh, climate change has stopped. That, at this point, is a political statement rather than a scientific one. You'll see that a couple of times along the way here. Okay, why is that happening? I think this is the basic answer. We'll look at a couple slides about this. This is the famous Keeling curve, named after David Keeling, former postdoc at Caltech, by the way. When he first came up with the ways to make these sorts of measurements, but really he made his career at the Scripps Institute of Oceanography. That's their symbol down here. And you can see here's 320 ppm going up to 400 ppm. from 1960 to 2000, up here, getting close to today. The first thing that you can see on here, besides the sort of mean rise, is the seasonal cycle. This is the terrestrial biosphere breathing carbon in and breathing it out. This is the summer, spring and summer, photosynthesis taking CO2 out of the atmosphere, and the winter and fall, respiration, that is the microbes and worms and everything living in the soils, breathing it back out, up and down the seasonal cycle, but the ever-increasing amount in the atmosphere from our fossil fuel emissions. Okay, I just wanted to give a little bit of perspective on that. This is what I get out of bed in the morning and do, is think about the history of Earth's climate and the paleoclimate. And so I have a few slides about this. It's a little hard to see this, but this is now 10,000 years, right? So I'm totally noodling with the x-axis on you here. This is several decades that we saw here. Now I'm multiplying that way out. So the curve that I just showed you is this one right here, that thick line right there. And these are geologic archives. This is an ice core. This is the fern, the part of the ice core that hasn't quite become ice just yet. It's still open snow. And you can see that the beginning of Keeling's measurements line up beautifully with our geologic archives. There's maybe not so much about this curve that you might find beautiful, but just from like a scientific point of view, it's kind of awesome, right? That the instrumental record is lining up with the geologic record. Yes, what's the question?
Is this an exponential curve then?
This is exactly this curve, and we'll see in just a second, it's equivalent to about a 2.3 degree warming for each doubling of CO2. Exactly where you see doublings along the way is roughly what's going on with an exponential, but it doesn't have to be that way, and one of the things I'm going to show you, I hope, is some of the processes involved in setting it, whether it's exponential or linear or rolling off. Yeah. Okay. So that's a great thing about Pasadena crowd, right? I can worry about, am I getting too technical? And then somebody asks me, is that a power law or is that a polynomial? What's going on? It's so good. Keep that kind of stuff coming. Okay. All right. So I have found, I was a chemist as an undergraduate, and I found it very hard to wrap my head around timescales associated when I came into the earth sciences. And this is the first one that's hard, right? How do you think about 10,000 years? All right, so here's first human agriculture. About 10,000 years ago, right? This is the Tigris and Euphrates. This is also going on over in East Asia. This is, we'll see in a little bit, you're coming out of the last glacial maximum, a time of rapid climate change, and climate is sort of stabilized, and this is when human societies settle down for the first time. This is kind of human cultural evolution related to climate. We motor along for thousands and thousands and thousands of years, and we get to the golden age of Athens, Periclean Athens here. This is when all the plays that you were forced to read in high school and college were written. I loved reading those plays, actually. Thucydides was also the history that's written about this particular time. Keeping with kind of early democracy, here's the Magna Carta. Magna Carta happens at about 285 or something like that, right? 280 ppm CO2. Then we come up this curve. Here's the last time the Miami Dolphins won the Super Bowl, which is incredibly depressing to me. This is probably the most depressing part about this curve for me, is that we were at 330 in the atmosphere the last time that I was able to celebrate a Super Bowl. I was actually quite young at the time that happened. Between here and there, we had Dan Marino as our quarterback, and we're unable to win the Super Bowl. The greatest quarterback ever to live, and there's no question about that, by the way. Okay, so this is the long time scale of suffering of a fan, but here's actually sort of the climate at work. Okay, so very clearly something is up. It's actually, we can put it into even more context. Now I'm totally messing with you, because not only have I made the x-axis even longer here. That's 800,000 years instead of 10,000 years. So the last thing I showed you was just right in here, and we're expanding it way back, and I flipped the order of the axis. So today is over here on the left, and that's just to keep you on your toes. Again, I'm plotting PCO2 here in blue, and the temperature, this is now a proxy rather than an actual thermometer measurement. This is the isotope ratio of ice in the ice cores turned into a temperature measurement. That's what us geochemists sort of love to kind of do. This is actually the CO2, though. The ice cores do a beautiful job of trapping little bits of the atmosphere. We can come back to them, break them apart in the lab. This is not my work. And I hope you've had a long enough time to see here that the pattern of CO2 going up and down looks just like the pattern of temperature going up and down. This is natural climate change, right? This is the waxing and waning of the ice sheets. Here's the last glacial maximum where there's 3 kilometers of ice on top of Canada. You're forming Long Island and Cape Cod here by pushing the rocks out in front of the ice sheet. There's all sorts of awesome geologic stories that we can tell here. CO2 and temperature are moving along lockstep. That's the curve I just showed you, put on top. That is about 400 ppm at the top of this, and I could not make this thin enough as a line to be the right time scale associated with what we know to be the natural variations over the last million years or so. I think this plot shows us a few things. The first is we are conducting an experiment of unprecedented geologic magnitude. It is absolutely an experiment. We don't know how it's going to turn out. It is the way that we are noodling with the system, and we are trying to decide what to do. If anybody tells you about how, well, it's been warmer in the past, the climate is cycled and all, those are all true statements, and they have nothing to do with what we're up against. They do in the sense that I study them to try to understand the physics of the climate system, and so what would ringing a bell like this look like if we could read these wiggles correctly? But that's for like me and 500 other people on the planet, right? Who are trying to sort of, I mean, you're welcome to come and try to do that too. We could use all the help we could get. But in terms of what we're going to do for society, this is pretty much become an engineering problem as opposed to a scientific one. We would love for those two communities to work together. I'm trying to wear both hats myself, and I hope to walk you through that a little bit as we go along. But I think if somebody tries to tell you that it's hard to know where natural climate change has been overtaken by human climate change, that also at this point is a political statement rather than a scientific one. It's not really focusing on what the hard problem is. One of the things I hope to give you out of this talk is that I have a huge amount of faith in this country and maybe even this country's ability to work with other countries, but at least just within this country, to solve hard problems. But we will not do it if we don't know what problem we're solving. And right now, we have a huge debate going back and forth about, oh, should we do something, should we not do something? That's incredibly frustrating to people who have ideas, who are ready to carry them forward on what to do. Okay, so here are a few other things about this that I think are helpful. A lot of the time, I put up a slide like this, and people say, well, how come the temperature hasn't rocketed up in the same way? Why isn't it sort of going along 1 to 1? That's a perfectly reasonable question. So here is coming back now to the instrumental record of CO2 and the instrumental record of temperature, where this is temperature now, and instead of time, this is the CO2 concentration in the atmosphere. And here's the data that I just showed you with CO2 and with temperature together. There's all sorts of short-term variability in here, right? This is weather. This is El Nino. These are all sorts of ways the climate can vary on short term, but it's absolutely true that there's a correspondence between the CO2 rise and the temperature rise. And there's no getting around it, and we understand the basic physics of why. It's really very simple. It was understood 150 years ago by Tyndall. That's just uncontroversial, right? Okay, here is what it looks like going forward. That's the same data that I just showed you, right? Here's 300 ppm. Here is a business as usual, and then the time parts are ticking off here up to 2100 under an IPCC business as usual like sort of scenario. We are warming the planet. The signature is already there, and we are going to continue to warm the planet with our CO2 output. I think that's just incontrovertible, right? That if you need these, I got most of these sorts of things on publicly available data off the web. You could actually go out and do the same sorts of things. I tried to sort of cite them down here. These are really, he has this as an animation, it's a Robert Rode, that is really fun to watch. I mean, I don't know which is fun, but it's really interesting to watch. Okay, so I thought, look, we're in Pasadena. I should find something that's a little bit more relevant. I think that Lauren did a terrific job of bringing these issues right back to local, and you guys did a terrific job of saying, you know, here's what I could try to do. Wait a minute, I don't think that that one's going to kind of work. So the Pasadena Water and Power Department published this paper. Kimbrough, I don't know, are you here, David Kimbrough? Maybe you were here. I've never met you, but this was a really cool paper. Where he went back through all the data, right? People have come collecting weather data for decades and decades and decades and decades, And he just looked at 1911, he looked at all the decades, but I pulled this one out, 1911 to 1920 compared to 2011 to 2016, nighttime temperatures in Pasadena, right? In the mean, it's gotten 5 degrees centigrade, right? 5 degrees centigrade hotter at night recently compared to the earlier part of the 20th century. In fact, I used to think, how did people survive here without air conditioning? They were way tougher than us. Actually, they weren't, right? It was literally cooler for them at nighttime when you were sitting there hot, lying in bed, right? This is what we're up against, and it's not just about these global trends, it's also quite local, but we heard a lot about that already beforehand. Okay, we know where that CO2 is coming from. We keep actually quite good records of this because it's directly related to our economies. And so I kind of like this, this plot. Again, we're going all the way back to 1800, coming forward up towards today, with gigatons of carbon per year. So this is a rate down, on this plot. This is an integral of that rate. So this is how fast we're doing it per year. This is keeping track of the total amount that's been added up as those rates have gone up and down. Two different things. And we can see the total, here we go, right? Here's the onset of the Industrial Revolution. Here's the American era post-World War II. Actually, all of these little jumps that you can see in here, this is the 70s oil crisis right in here. This is the savings and loan crisis. Each one of these little ticks away are things that you know about because the economies were changing, right? This scales directly with global economy. You can see some other really cool things in here. So that it's broken out into the type of fuel. Solids are basically coal. Liquids is essentially gasoline. This is natural gas. And then, of course, cement production does something too. And so the Industrial Revolution was all about coal, right? And then here is the onset of gasoline. But you can see coal has a comeback. This is the Chinese coal revolution powering up their economy as well. And so you can kind of see some neat sort of geopolitical features going on there. The only thing the climate cares about is this one. The climate cares about how much total we've put in. And this is something that is sort of lost on a lot of people, a lot of really smart people, right? And I think the way to think about it is your credit card, right? You build up a balance, a debt on your credit card, right? You've been spending too much, and you go, geez, I really got to do something about that. Not that that's ever happened to me. And you figure out a way to get your cash flow back in order, right? Your sort of month-to-month cash flow back in order, and you feel, excellent. And you still have thousands of dollars of debt sitting there that you're paying for at an interest rate. Hopefully not on a credit card interest rate. You should transfer it to something else if that's true. The climate is doing exactly the same thing. If we get ourselves to net zero emissions, that is an unbelievably cool accomplishment, and we're not done. I hate to tell you, because we've already baked all this in, right? You still got to pay down all of your credit card debt. You can't just get your cash flow in order. You've got to pay down all of the debt. And that's why we're here talking about sequestering carbon, or how to take carbon up. Okay? The climate cares about this one, not this one, but this is the one you hear about all the time. All right, so what is up with this, right? How has the carbon system, how does it work, and how has it changed given all this extra carbon that we've burned and put into the atmosphere? There are all sorts of numbers and arrows and things on here, so I don't expect you to ingest this whole thing, but basically there are two types of numbers. There's the size of something, so this is the reservoir of vegetation and soil detritus, and then these are the fluxes in and out. And one thing I think that's really important to keep track of, look at some of the sizes of these numbers, right? 1.6, 70, we could go and identify them. The biggest ones here for fluxes in and out are gross primary productivity, that's plants, right? That's photosynthesis at work, taking CO2 out of the atmosphere at 120 every year, and respiration at almost exactly the same number. So this makes it a really hard thing, right, to kind of monitor and figure out. You have massive fluxes of carbon going back and forth that are almost exactly in balance. And we're trying to see what happened to the fossil fuel part as, that you've added to that on top of the cycle. Right? That's the Keeling curve going up that we have fossil fuels on here as well, sitting here at 6.4. And so really innovative tricks. The whole Keeling family seems to be doing this. Dave Keeling's son, Ralph, came up with one of the most ingenious ways to do it, to measure oxygen in the atmosphere really precisely to go along with carbon. And so we actually have a very nice grip on some of these numbers. But I just want to give you a sense of how it would be very easy to lie to you, like with statistics, right? By cherry picking some numbers out of here to say, oh, things aren't going up nearly as much anymore. If there was a little bit of an imbalance in here, there could be a massively big number in the biosphere compared to fossil fuels, and you betcha people are paying attention to that to try to change your mind to not think about climate change or not think about CO2. It is really easy to get tricked in this, and I'm sort of hoping to give you a little bit of background information so you can see through the noise on just the sort of what is the problem that we're up against. Okay? All right. So another way to look at that then is how has the natural climate system taken care of the fossil CO2? So instead of all those natural things, those huge arrows going back and forth, there have been various tricks to try to measure how have the sources and sinks changed over time. So this one I showed you, we know this very well from economic data. Here's how much is coming up from fossil fuels in industry. This one, this sink, ocean sink, is a measurement. It's a measurement that isn't done all that often because the ocean's really big and we have small boats, right? And so you have to go and collect the water and then measure the carbon in the water. We don't have a good satellite for carbon concentration in the ocean. Maybe some of you guys from JPL will figure that one out. And so this is this doesn't have very sharp amplitude wiggles to it because we're just now learning how to use satellites to get at this indirectly. Okay, the atmosphere, this is another measurement, right? We can actually just measure the CO2 that's up there in the atmosphere, and here we have created good satellites, one of which is the OCO2 has developed through JPL, really an incredible new piece of machinery. The Lynn Center where I work, we actually have one of the calibration stations that is the old solar observatory in the Lynn Robinson building that maybe many of you drive by on California that was built to attract hail to come to Caltech. We've repurposed that as we still follow the sun as we go, but we repurposed that as a spectrophotometer to calibrate the CO2 satellite that's sitting up there. It's really cool, right? Okay, then the land is done by difference because it's really hard to measure this. You have to go measure the change in the width of every tree on the planet, right? Or you have to go measure how much you have to go figure out how much has the land changed relative to the fact that it is the biggest fluxes in and out and they're almost exactly in balance. And so these two numbers exactly add up just because of the way this thing is constructed. It also means the land looks like it's the most dynamic part because it has to be the thing that it comes into balance. And it's not clear that the ocean might actually be just as active in the surface ocean. We just don't have the measurements to see it. But in general, we're able to understand that about a third of the CO2 of the total CO2 that we burn, about a third is taken up by the land, about a third is taken up by the ocean, and a third stays in the atmosphere. And so the natural system is already doing 2/3 of the job for us in that way, right? And yet, the Keeling curve is what it is, and it's going up, and temperatures are still rising. That's another good way to get tricked, right? Is that people will sort of say, well, look what all the natural systems are doing just fine. It's not clear that they're doing just fine, but they are actually responding to the perturbation that we're putting in the system, and they're responding this way. Here are some ideas about various scenarios for how we might do that. So these encompass thoughts about business as usual or thoughts about doing something different than business as usual. Let me just explain this briefly. This is emissions from fossil fuels and cement. So this is, again, a rate, not an inventory, right? This is how quickly or how much carbon are we releasing in gigatons CO2. We're sitting at something around just under 40 gigatons a year right now from 1980, and then projections going forward at 2100. So historical data, this is just data sitting right here. And then this is model stuff, right? This is take climate models coupled to economic models and have a business as usual scenario. Then one idea, and these are the ensemble of them, right? All the little thinner lines down here, all sorts of different versions, is that you warm by 3 to 5.5 degrees by 2100. This is the only one that meets the Paris goal. And a lot of it doesn't meet the Paris goal, right? And so every one of these scenarios includes not just reducing our emissions, but taking CO2 out of the atmosphere. And so this is kind of a nice plot that is sort of making its way into cultural consciousness, but I think that something is missing. It makes us feel a little bit too sort of like, okay, great, right? All we have to do is start reducing our addiction to fossil fuels. We absolutely have to do that, don't get me wrong. That's a huge part of these curves, but the only way they actually come down is that we take the CO2 out of the atmosphere as well. Those are not technologies that are scaled just yet, but I'm going to show you a few of them that are at work. So there have been a bunch of studies about this. We're going to move into the sort of the carbon dioxide removal process. This is an unbelievably boring subject, right? And presented in really boring ways. And so I'm going to communicate that to you by boring you for a couple of slides here. This image is from the Virgin Earth Challenge. So this was Richard Branson putting out there that he would give $1 million, right, to, right? It's laughable in how small amount of money it is, right? To somebody who comes up with a solution to how to store carbon, right? Because this is the largest economy on the planet, right? It is trillions and tens to hundreds of trillions of dollars, the energy economy every year. To give a prize that's $1 million to somebody who's just discovered what's going to be the origin of a carbon tax or a price on carbon was sort of crazy. But they put together this really beautiful set of state of where things are at, circa 2014 or so. And so I stole this image from there. There's a lot of good information in their packet that they put out about this challenge. Basically, you can try to stimulate biology to take out the carbon, or we can come up with chemical and physical ways of taking out the carbon. There are a whole variety of ways that you might store it, right? Here's soils that came up earlier. We could make solid products. You can go pump it down into geologic storage. Geologic storage appears twice, as we see over here, and then that's sort of how this can get complicated and in some sense just sort of mind-numbingly boring. As the fingers come down here, it gets more and more technical, and there's actually more and more sort of overlaps to them. And so I wanted to just kind of give you a sense of the various themes that are true for all of these ones. So a little bit of a roadmap to kind of keep track when somebody brings up their next favorite carbon removal one. The National Academy of Sciences has just released a report on how to do this. It was chaired by Steve Picala, a professor at Princeton. It literally came out just a couple of months ago, and their main chapters are these 5. And I have to say, this is an oddly specific set of things to study. This is what's supposed to set the research agenda for the country for what to do about this. It's publicly available, this report. One way to point out about this is that this says absolutely nothing about the open ocean as a way to store CO2, which is 70% of the Earth's surface. And it just seems like an odd choice if we're going to try to think about engineering solutions to say we're only ever going to do things on land. That is something I'd be really interested to hear feedback from you guys about, right? Because I'm an oceanographer, and it seems sort of obvious to me. And yet, for some reason, for a decade or more, the oceans have been off the table as a way to think about how to sequester carbon. Even the National Academy set it up that way, and I would love to understand why that is. Okay, so there are a few really sort of straightforward things. You'll hear a lot about DAC, or direct air capture. It is really simple at its essence. Move a lot of the atmosphere through your reactor, and then in little pipes, take that carbon and go put it somewhere else. That's it. That's it. Capture it directly out of the atmosphere. Direct air capture, right? It is going to require massive setups of, this is from carbon engineering in Canada, this picture here. Okay, there are two, climate engineering. There are two really main viable companies that are doing this kind of thing right now. Climate engineering in Canada, Climeworks in Switzerland. I don't really want to sort of walk you through these kinds of things, but these are both chemical solutions. They're sort of combination chemical and physical solutions, and they take some energy in or they take some water in, and they make pure CO2 out. Of course, that's just capture, right? All you've done now is taken something that's kind of dilute in the atmosphere and now made it much more concentrated. If you're done, if that's the end of your pipe, it just goes right back out into the atmosphere. You have to then go put it into something. And so Climeworks is actually selling to soda companies to carbonate the CO2. That means you're actually going to burp it back out eventually, right, after you drink that soda. But at least it came from the atmosphere in the first place and not some fossil source of CO2 that was down there. Climate engineering is very focused on making fuels out of their pure CO2, with the idea being that, yeah, so anything you do to make fuels out of CO2 that already exist in the atmosphere that's carbon that you didn't have to take out of the ground, and yet you're still allowing yourself to drive a car in the way that, we won't get into the okay, so direct air capture is just as it sounds, but it's only half of it, right? It's only getting it out of the atmosphere, it's not storing it in the ground. So carbon storage is also happening now, right? And there are a variety of ideas here, but they're all essentially the same idea, is take whatever that source of CO2, that like sign up with David Keith's carbon engineering company, and then pump it into some geologic reservoir so that it doesn't come back out. I mean, these are really pretty straightforward things, right? And absolutely the kinds of things that we should be thinking about trying to do. However, also in this geologic storage options, we sort of seem to leave the ocean behind. This is a quite popular one, and there are various versions of it, BECCS, and this highlights, I think, some of the really important sort of global fluxes that are going on. Everybody talks about how the best carbon storage are trees or plants, right? And you can even buy offsets for flying on airplanes, right, that go plant trees. That is great in the short term and does almost nothing in the long term because they're termites, right? And they're microbes, right? All of that biomass that gets made into a tree that takes CO2 through photosynthesis and stored into a solid eventually goes back up at CO2. One way to think about this is what's the mean age of a tree, or what's the mean age of plant matter on the Earth? The answer is a few decades. So that turnover time of photosynthesis is one that all that extra stuff that we're doing to take into plants is just going to come right back out at us, right? The other thing that you have to worry about when you do things like this is that it's not just about carbon. They take up water, they take up nitrate, they take up phosphate. You have to think about the other pieces of the geochemical cycles that are required to make them. However, they're incredibly good at doing it, right? So like, let's not sort of forget that part. In fact, you could grow plants on purpose to burn them and run a power plant, right? Get electricity out of spinning a turbine from having, instead of burning coal, right? Instead of burning fossil fuels, natural gas, right? Burn the plants that you grew. And now it's much easier to put things into this smokestack to capture the carbon in the first place. So the plants have done the job of diffusely capturing the carbon out of the atmosphere via photosynthesis. Burning it makes a very concentrated stream, 5 to 10, 15%, something like that. And then take that and bury it into the ground, right? And that's a way that you can get the energy associated from the sun to power the photosynthesis back out into the grid and still put carbon atoms back into the ground. There are a dozen different permutations of this out there as ideas to do, and you might hear various versions of them, but they all sort of run around in this way for BECCS. Okay. So rather than try to sort of go through this long list, I was tasked with this job of teaching you guys about carbon sequestration. I thought I would show you our own idea about what to do. We've had a kind of technological breakthrough in the lab, in my lab at Caltech. And I thought I'd show you some of the things that we're up against as we think about, is this viable or not, and how might it come about, as sort of a case study that you could apply to any one of these carbon storage sorts of mechanisms. So the first point is, as geochemists, we actually know what's going to happen to the fossil fuels. Because this reaction, CO2 plus the calcium carbonate that makes up ocean sediments, has been buffering changes in CO2 in the atmosphere to make the ocean a little saltier for billions of years. Right? This is one of the key buffering reactions on the planet. It's one of the main reasons that we're not Venus, right? Where all the CO2 has been blown off and that we don't have There aren't calcium carbonate rocks on Venus the way that we have them here. This kind of cycling of carbon between gas, liquid, and solid is a buffering reaction that has actually kept climate equitable on our planet for billions of years. And in fact, on those sorts of timescales, it's quite a fast buffering. It's tens of thousands of years, right? Super fast. That's why you don't hear about it, right? Is that as something that is going to save us from ourselves, right? This is a way that like Mother Nature would be saving us from our own bad habits, right? From our not paying the price of the garbage that we put in the atmosphere, which I think is one of the best ways to think about CO2. Is we currently have been getting power without having we have been creating garbage without having to pay somebody to take it away for us, right? That was also true in medieval cities, right? For literally solid waste. And nobody wanted to walk around in medieval cities. It's why we have waste hauling companies now, right? As we decided it was a community good to pay money to take away our garbage. We've been having a free ride, fossil fuel companies included, but really us too, right? We're the ones paying for the energy, have been having a free ride. The planet will save us over tens of thousands of years, which is to say it won't save us, right? We're gonna really bake ourselves long before we do that. And this is slow for a variety of reasons, but we actually stumbled across a catalyst for this reaction a couple summers ago in the lab. And so this is the rate at which the reaction is going versus an unintelligible axis that is about being more acidic over here and more basic over here. The main point of this is that this is a log plot. So to go from -7 to -6 is a factor of 10 change. It's kind of like the Richter scale, right? Like you don't pay any attention to a earthquake magnitude 5, really. It's like, oh yeah, that maybe gets on the news. Earthquake magnitude 6, and it's a disaster, right? Well, this is the natural, right, regular background rate at which that reaction goes. And this catalyst, this enzyme that we found, makes it go 500 times faster in the lab. And so the idea is to try to harness that in an engineering way to use exactly the natural reaction that the planet is going to run to match the acceleration that we've done by taking fossil fuels out of the ground. Okay, so, and I do this to upset my British friends, we're going to take the White Cliffs of Dover, right, which are made out of calcium carbonate, or we're going to take the Carrara marble mines, right, from which David was constructed in Italy, and we're going to react them with CO2 coming out of smokestacks or even ambient CO2 that's around there. Both ideas might work, this one in freshwater, this one in seawater. And together, we're going to put those two together and make saltier water. Just like the planet will do, but we'll just make it go faster, as fast as we're accelerating the other process that has a natural analog, the burning of fossil fuels. Okay, so here's one of the very first problems that we have. How much, right? How much do we need to do to solve the problem? How does it scale? Well, to keep up with that 40 gigatons of CO2 that we did last year, we need a cube of limestone 2 miles on each side. That turns out to be a lot of limestone, right? So one reason I kind of like this, I mean, I like this, don't like this, doesn't really matter if I like it or not, this is what you need, and that's the point. Every single one of these technologies that you come up with, the scale is enormous, right? That is not a reason to run from the problem. That is just what we're up against. In our particular case, the way we phrase it is this giant block of limestone. There is plenty of limestone on the planet to go and do this. That's not going to be the limiting problem for this particular, for what we're up to, but it does give you a sense of the scale. If I tried to do this reaction at the rate that we've done it in the lab, and I said, I'm going to do it in a Walmart superstore size factory. This was a fun day on the web. I was sort of looking around for the right analog for this. Then uncatalyzed, you would need something like 24,000 factories to run this reaction, and that seems like a daunting number. Catalyzed, we need about 600. There are over 3,000 Walmart superstores in operation right now in the United States alone. Moving trucks back and forth, goods going, right? It has actually a few analogies that help us, right, with the sort of scale of a thing that we'd have to pull off right here.
So you're talking 600 factories around the whole world?
Globally. Yeah. I did this calculation. Actually, I was really excited that we found a catalyst for this reaction for all sorts of nerdy, like physical chemistry reasons, right? And it was taking a shower, getting ready to coach my kids' AYSO teams right here in Pasadena, that it dawned on me, oh wait, we've made the reaction go faster. And I jumped out of the shower and did a version of this back of the envelope calculation and realized, whoa, it is not crazy. It is not small, but it is not crazy to think about this as the right way forward. And what I liked about it is that this is the reaction the planet's going to run anyway. The planet is not going to take CO2 and store it back in a reservoir down underneath the ground. It's going to do exactly this, right? But this is a massive new industry that doesn't currently exist, right? So it is daunting in what we're up against. Just to give you sort of a sense here, currently the largest industry on the planet that mines limestone is the cement industry, and we would have to increase the rate at which we're mining limestone by over a factor of 10, maybe something more like a factor of 50 to keep up. That's huge, right? It's a sense of the scale of the problem. This is what we have done so far, right? If you say, oh, I don't like that, well, we get warmer, right? It's just like, that's it. That's what we've got to do. Like, if we're not clear-eyed about the problem we need to solve, we're never going to solve it. Okay, so here's what we're doing. This is ridiculous, I realize. But so we started trying to run the reaction in the lab, right? So we tried to take a water pump and some water with or without the catalyst, bubble it through some CO2, and then push that through a column of limestone. The cardboard box is ridiculously important to this whole operation, right? To actually work. I don't know what to say. This is like innovation in action, I guess. You just sort of grab things that are around and you try to see what you can do. We have been able to take CO2 that if we don't put the catalyst in the water, here's how much CO2 comes out. And if we do put the catalyst in the water, here's how much less CO2 comes out. We started with 10,000 on this scale over here, right? So even here, we're doing it, even without the catalyst, we're actually doing a job of taking CO2 out. The catalyst just sort of helps you go faster. It's totally cheesy, right? But it turns out this is good enough to get a patent, for whatever that means. Okay, so what we're doing these days is we've built different shaped reactors, a fluidized bed reactor, and this is the smokestack at Caltech's 10 megawatt cogeneration plant that exists right on Wilson. It's the noisy thing. If you're driving south on Wilson, it's just sort of like, why did something get noisy around here? That's Caltech making electrons, right, to go power everything. And the CO2 associated with that comes out of this one stack, and the physical plant group there has been really terrific. This now has a bar going in through that hole right there, and we're sipping actual CO2 off of a real power plant to see how well we can do as a test bed, to go back and forth with things that we try at the lab bench with the cardboard box to actually come and try it out at a real power plant. Okay, here's an idea that I hope Lauren will love. I talked to her briefly about this at the break. Everybody recognize where this is? Yeah. Yeah, exactly. The LAX is just here, right? This is the Hyperion reclamation. There's LAX. Here's the Hyperion wastewater plant, right next to Scattergood, the base load power plant for LA, right? Huge plant, 800 megawatt. Used to be coal, now it's natural gas, right? Well, I like that. Here's a source of CO2. Here's a source of water that's already going way offshore, that already is being treated. I want to hook these two up, right? I want to run our reaction. I want to bring limestone, bring calcium carbonate into this system, and send a little bit saltier water down the pipe of Hyperion. So what would that look like? Well, that's not what this is. These are just pictures of the two of them, right? But this has about 10% CO2 coming out of these smokestacks. We'll do some flue gas transfer over here to what seems like a very large number, 275 million gallons per day of wastewater going out of Hyperion, right, down a very long pipe designed by Caltech scientists in the previous generation. That seems like a big number. Okay, so if I take the total carbon that I think I can put into it, right, how much fresh water do I need to keep up with the 40 gigatons if I'm going to make 10 millimolar concentration of carbon in the water? It turns out I need just a little bit less than all of the river flow on the planet. Right? Oh my God. Right? So, right, fresh water is precious, right? Fresh water is a very precious resource. Nobody knows that better than Southern Californians. Maybe Southern Italians know it just as well. I'm sorry if I'm doing that. I don't know what the story is with that. So while locally, this would be great. This is not a reason not to do it. This water source already exists. It's already our wastewater treatment plant. We should try to go do this, right? But there's no way that this is the thing that's going to scale to give us all 40 gigatons. Well, one solution is not actually going to be the answer, right? I don't feel like, I would love to do the whole problem of 40 gigatons, but if I did 10% of the problem, okay, right? Like I could be comfortable with that, because I have 10 other friends who have 10 other ideas, right, to get to the whole problem. Ultimately, we're going to have to do this in seawater. Seawater is unlimited in its capacity to take up the effluent of this reaction. That doesn't mean there aren't serious issues to think about the effluent, especially right at where the pipe goes. I'm not trying to sort of paint those over, but these are global, everything's well mixed. How are we doing with sort of solving the whole problem? Seawater absolutely has the capacity to pull this off. We're going to need something like cargo ships going out and mowing the lawn and running this reaction as they go. Okay, costs, right? What are we up against with costs? Well, we have to do a few things. This is just a schematic of like a swimming pool that's on the site of, say, of Hyperion. We have to bring CO2 in. We have to pump water uphill, and we have to mine, transport, and crush limestone in order to get it there. And so I hired a civil engineering company to cost this out for me, and the answer is $60 a ton of CO2. I have no idea if that number means anything to you. This is a thing that is getting debated a lot now, that it bubbles up into the Times and the Post that you see in places. What if you had a price on carbon, either through a cap and trade system or through a tax in whatever way, what should it be, right? Those answers, the EPA did a study about this, it comes in at order $20 to $30 a ton or so. Darn it, right? I'm at 60. I was happy I wasn't 600, to tell you the truth, right? In these early days, it's felt like, okay, we're getting close. Over half of it is the limestone cost itself, a big chunk of which is transport, and so if I switched from rail transport to barge transport, this number already starts to come down. But I think market-based solutions must be part of how we do this. That's the beauty of having a price on carbon as you go. And all of us who are thinking of innovative ideas have to simultaneously think about how this fits into any new market that might be created. We're at about $60 a ton, minus the cost of the catalyst, which would crush us. Some advantages or things that we're sort of up against, I think this is maybe the one to pay attention to. This is not, there is a line across here. Maybe it's this one down here. We're putting hard water out. That's this salty water that we're putting out is hard water. It's the same stuff that it used to appear on your dishes all the time when you just dried your dishes on the side here in Pasadena. Half of the year, right, these calcium carbonate deposits would be there. That's the hardness of the water. That is a regulated commodity, as it should be, not commodity, regulated effluent, especially for power plants. And we would come out at something like 5,000, and we need to be down here at about 1,000 before it's unregulated at all. But the solution to that is just dilution, which power plants are already doing. Single pass cooling power plants have to worry about the temperature of the water they're putting out. They're diluting orders of magnitude larger than that already. And so this is one version of how do we think about the effluent. Okay, the last slide here, really. We've done this kind of thing before as a society, right? I've thrown some big numbers. It seems sort of scary. This is the sort of problem that we've gotten ourselves into. If we decide that there's a problem, we're unbelievably good at turning to and trying to figure it out. The Clean Air Act is an excellent example of that, right? So here is lead, the concentration of lead in corals in Bermuda from 1850 up to 1990, right? This is the onset of the Industrial Revolution, again, the American era. 1972, 1971, the Clean Air Act came out in a variety of phases, but the main one is right here at the top of the curve. It was in order, that it started as a way to get rid of leaded gasoline, right? At lead, as soon as we turned that around, the corals felt it, and the concentration of lead in the corals out of Bermuda started dropping. This is, I think, one of the great sort of geochemical or geological plots that show that good legislation leads to good results, right? We've also done it as a tax before, right? With who remembers acid rain, right? Yeah. Do we talk about acid rain anymore? Cap and trade helps solve that problem, right? Now, there was a technology ready to go, right, already there from the industry, so it's a little bit of a fake analogy than what I'm giving you, but here's tons of SO2 emissions. SO2 was the source of the acid rain, 1990 to 2002. This is under the first President Bush, right? Said, yeah, we'll have a cap and trade, right? And here's what the emissions are over time. Here's what everyone thought the projected costs would be to run this program. And here's what SO2 actually ended up costing. The program actually ended up costing as it went along. And the Adirondacks are no longer being acidified by power plants in the Midwest. Through market incentive programs with government control, the cap, that's a tax, right? That's a government control. That's society saying this is what we think is important about what we do, but companies responding in order to still try to make money off of generating power in the Midwest. Thank you very much. I'd be happy to take any more questions.
This is a question I was wanting to ask the others before this, and it has to do with the 100 solutions that have been aggregated as the drawdown.
Mm-hmm.
Are you familiar with those solutions and the concept of drawdown?
I think I am, but let me make sure that I'm not getting this wrong. But I just knocked myself out of the presentation. But I had that slide where there was a business as usual and the CO2 rates went up. And then there were other scenarios where the CO2 emission rates came down. That's the drawdown, right? That is, how do we pull CO2? How do we emit less and pull CO2 out of the atmosphere? After this National Academy report, you're going to hear this be called NETs a lot, negative emission technologies, right? And then quickly the reporters are going to just start calling net this, net that, and it's going to be hard to understand. The drawdown is negative emission technologies.
Yes, and this particular set of solutions was researched by 200 researchers, peer-reviewed, empirically founded, with the goal of reversing global warming by 2050. And I think in terms of the political mountain, changing the paradigm to reversing global warming will help with that, because we've been doing experiments with classes of people, and when they hear we can reverse global warming instead of mitigate or slow down, there's a big change in people's motivation to do the things we're talking about.
I think that's just a terrific point. Like, the more we can do to motivate people to solve things rather than shame them about what they're doing, the better off we're all going to be. I think that's a great point, Tuck. Yeah.
Move up closer.
Yeah.
They want you on camera, Mike.
Okay.
Yeah.
Jess, can you remind us this reaction when you bring the CO2 together with the calcium carbonate? What are the products of that reaction?
They are bicarbonate and calcium, so that doesn't necessarily help so much. So let me try to put that in context. Calcium is part of what goes into making coral skeletons, right? The coral skeletons are made out of the calcium carbonate. The bicarbonate, the salt of which is Arm & Hammer baking soda, right? So you might have this in your refrigerator right now in the little yellow box, right? We do, because we have smelly food. But the main point is those are the main constituents of salt in the ocean already. Mm-hmm. And so that's why I say our effluent in the long run is just a little bit saltier water. That there isn't a community out there, right, that might like bicarbonate better than something else that might take off, and so we've perturbed the ecology, that's totally on the table. We have to study about that. We can't just say, oh,
you mean a biological community?
Yeah,
like
biological
organisms
community. That's right. But one thing I do know is that from the chemistry of the ocean, we will not change the pH 1 iota. This will neutralize the ocean acidification that's already going on as another part of the CO2.
Okay, thank you.
Yep.
Thank you. Great presentation. Real quickly, you had a slide about your economic analysis for doing this with the scale up looking at 40 gigatons of carbon at something like 8 cubic miles of limestone. Did your analysis include the energy cost of mining, crushing, and transporting that?
Yes, that is part of the limestone cost, and one of the keys there is we used about, I think it said on the bottom of the slide, ½ cent per kilowatt hour to pay for the electricity that we needed, but yeah, we didn't leave that part out. Yep. Thank you guys, I really appreciate you coming out. Have a terrific weekend.